Well, good afternoon, everybody. Welcome to the MTL seminar series. Today, we have two excellent speakers from Draper Laboratories, Gregg Favalora and Moebius. And the title of his talk, their talk, is going to be Electroholographic 3D Display Technologies based on surface acoustic wave modulators in lithium niobate oxide. Gregg is the group leader for sensors and imaging systems at Draper and has been an engineering and R&D manager of optical systems for over 20 years. As a specialist in 3D display technology, he co-chairs the Stereoscopic Displays and Applications Conference and was founder and CTO of Actuality Systems, creator of volumetric and other 3D displays. Gregg received the Bachelor of Science in Electrical Engineering from Yale University, Master of Science in Engineering Sciences from Harvard University, and is an inventor of approximately 20 US patents. So welcome, Gregg.
Thanks for having me.
Oh, thank you. Moebius is a senior member of the technical staff in Draper's Photonic Systems Group, where he has been working on programs developing integrated photonic device solutions in a variety of applications. Michel's expertise is in modeling and design of photonic systems, and his previous work included nonlinear photonics and 3D direct laser writing. Michel is from Germany, and he received a PhD in applied physics from Harvard University and a Bachelor of Science in Materials Engineering and Applied Physics from Rensselaer Polytechnic Institute. Welcome, Michel, again. Thank you for accepting our invitation to give a seminar, and the stage is yours.
Okay. So thank you so much for attending the seminar today about holographic video technologies. As you heard, Michel and I are from Draper, which of course is located right in Kendall Square. And this is a presentation about the culmination of a 4-year-long internal R&D effort to really try to push the boundaries of 3D display technology. I'm the PI of the effort and have spent about 30 years or so in the field. And one thing I learned is that a primary enabling technology is the light modulator. So of course, microfabrication and integrated optics really drive those capabilities to enable systems like this to be created. So today's talk then is electroholographic display technologies based on surface acoustic wave modulators in lithium niobate, or in plain English, emerging technologies for truly holographic 3D displays. Over the 4-year effort, many people contributed, 30 or 40 across quite a wide display of disciplines from Draper Lab, from microfab to video electronics. And getting to the punchline, what you'll learn a lot about today is electronic holographic displays. We will explain through the course of this talk the array of technologies that you see here, which did culminate in successful projection of both real and virtual imagery from this interesting emerging modulator type. You'll learn a bit about 2 variants of how you would use these AOMs for holographic display. One are called edge-emitting modulator-based displays, as you can see in the upper left, and the other is surface-emitting linear holographic displays, which get at sort of a more tablet form factor. So stepping back a bit, you might ask, well, why do you want to use a 3-dimensional display? And in our opinion, opportunities for projecting spatial 3D imagery are everywhere. So most 3D images or information can unlock value by being either task enabling, such as for time sensitive or mission critical applications, or being visually engaging. So for example, a holographic sand table for military personnel who are watching a mission unfold, just like you'd see in a science fiction movie, or surgical guidance, providing a cardiologist with the ability to watch cardiac catheterization for electrophysiology. Also, there are applications in dashboard and cockpit displays, oil and gas exploration, and so forth. But all of these things are usually presented in 2D display, even though in many cases 3D information exists. And it seems like there's a good opportunity here, both to help users and also a business opportunity. So to help bound this, for those of you who don't normally track the world of display technologies, it's estimated that the display panel market itself is almost $140 billion market per year with a healthy annual growth rate. Likewise, as a proxy, the military HUD market is very strong, as is just digital signage generally, which plays really large in retail. So what if, we ask, high-quality electronic holograms were a reality? So let's get into that. 3D displays and holograms are part of a branch called autostereoscopic 3D displays, which is 3D display technologies that look 3D to your unaided eye. So unlike when you go to one of today's 3D movies where you have to wear polarized glasses, auto stereo means that it looks 3D naturally. And there are quite a few of these types of displays. So although you can't go in the store today and just buy a wall-sized truly holographic display, as you might see in any number of movies like Iron Man, there are a variety of ways to produce imagery that looks 3D to the unaided eye. So there are about 35 ways to accomplish it. That would be a whole seminar in itself, so we'll just kind of touch on the most prevalent few. The main category of 3D display provides perspectives or views to the eyes of a viewer or multiple viewers at once. And usually these work by trading off the number of pixels, such as the pixels of an LCD or an OLED panel, across a number of viewpoints, say 8 views or 20 views. And the more views you get, especially if they don't overlap, is the more sharp depth that you can enjoy in an image. So those techniques are called spatially multiplexed because they trade off pixel count for views. That is, the more views you want, the more depth you want, the lower and lower the resolution the customer sees in that 3D display. So types include lenticular displays. Maybe you've seen these as novelty items or some of the better ones that are on the market now, or a variety of so-called directional illumination systems, such as the video game device shown on the right. But fundamentally, these approaches are from the early 1900s. They have improved recently, though, so we'll look at 2 of them. So on the left, you could see a parallax barrier display. When the observer is in the right location, a series of opaque slats, either in front of or behind the pixels, ensures that each eye only sees the appropriate 2D subimage. So you see 3D when the left eye sees the left eye pixels and the right eye sees the right eye pixels. Where on the bottom left is this lenticular display approach, which uses little lenslets instead of opaque bars, and that's more light efficient. So until recently, these spatially multiplexed 3D displays have offered imagery with limited depth, maybe an inch or 2, maybe more when they're really well done. And now they are improving radically because of the availability of high resolution backplanes. But that said, there will always be this trade-off between the spatial detail that you see in the image and the number of perspectives you see, which again is essentially the depth of the image. And people like to have really deep 3D imagery. So going on, here's a view to really bring this idea home, which is that ultimately 3D displays need numerous and non-overlapping perspectives. So here on the bottom left is that lenticular that I showed, where little groups of subpixels are all bounded together with a lens that then redirects the ray direction to the appropriate viewing direction. Whereas, and now we put an observer and their eyeballs up at the top side of the slide here. Whereas on the right, a holographic display, like a holographic stereogram, emits numerous perspectives from each region of the display. It's another story how you partition the display into these emissive regions. One way to do it is through holographic pixels or Hogels. But the point is that the centuries-old technology trades spatial detail for depth, whereas holographic displays have a lot more flexibility in how that's done. So I've told you that we're talking to you today about holographic displays. There's uses for them, and a number of non-holographic display technologies exist. Let's kind of focus on the holograms now. Holographic video displays rely principally on diffraction phenomena to display 3D imagery. And I want to drive that home because you've seen many vendors use the word holographic when there's nothing or next to nothing diffractive about the underlying system. So I like to focus on that. Something that you've probably seen in physics classes, or maybe you've made these on your own, is on the left. These are film or emulsion-based holograms. This example here is off-axis display holography from the 60s. And then to vastly simplify, there's a recording phase, and then there's a playback or reconstruction phase. In recording, you place an object near some special holographic film. You illuminate it with an object beam whose light then strikes the film. And you also apply a mutually coherent reference beam. These two things interfere the surface of the film, and so-called holographic fringes are developed into it. And it's important to note that the spatial detail level there is on the order of wavelength of light or greater. Then to replay it, after developing the film, you just quote unquote, just shine the reference beam on it or the playback beam and you can enjoy the resulting 3D image. You can do these things electronically too. They're just very, very different and use different terminology. So for example, you could take a high resolution spatial light modulator, like those little mirror chips or liquid crystal chips that are used in projectors. You could load in fringe data into it and then illuminate it with the light source, and it works. However, the imagery is usually small unless it's tiled, and the field of view is extremely narrow because the pixels are very large compared to the wavelength of light. An utterly different approach, which is something that largely was pioneered at the MIT Media Lab under Steve Benton, the late Stephen Benton, uses acousto-optical modulators. You can take crystals such as tellurium dioxide, whose properties change on the application of RF or acoustic energy at certain frequencies, to impart a shape and curvatures and detail to the light leaving these modulators. So these can be embedded inside of systems with multiple scanning mirrors to provide a floating 3D image to a viewer. So an emerging approach towards true electronic holography lately is SAW modulators, surface acoustic wave modulators. And Mikhail, in a few minutes, will go through quite a bit of the physics about how these things work. The high level view is SAW modulators are optical devices that map the frequency content of an input electronic waveform into the angular weights of output fans of light, typically horizontal. So that is, you do some computations, you apply some waveforms whose bandwidth takes up between the 300 and 400 megahertz band, and light comes out where naturally 50, 100, 200 different brightnesses as a function of angle can be seen. And you could see without much imagination that if you were to array these things together, you can then create a floating 3D image. And a beautiful thing is that the number of views, the number of resolvable spots, the things that really help you express depth, relates to several factors like the RF bandwidth, so-called interaction length, and also the speed of the surface acoustic waves that are zipping through this crystal. So I will sort of set the stage here by explaining one of two architectures we'll talk about today. This uses those SAW modulators, the surface acoustic wave modulators, in an edge-emitting variant. So here's what we proposed back in 2016 or 2017 when we were seeking internal R&D money to pursue this, which is an edge-emitting display. Shown here is a chassis populated with these vertical cards that we call light field projector modules. They take light as input and electric signals as input, and as output project horizontal ray fans, which when all of this is in operation, different eyes of the observers can see different aspects of the imagery at once. So to begin, analog waveforms induce these SAWs that when illuminated provide fans of horizontal perspective. So again, you line up an array of these like the spines of books on a bookshelf. Each card has modulator channels in it, which terminate in something you could colloquially call a pixel or a hoggle. Natively, these output 10, 15 degrees or so into air. So it's normally followed, in our case, by another optical layer, which is a tiny array of micro telescopes, which serves to increase the field of view of the light field up to 45 degrees, the design of one of which is shown in the upper right, as well as a polarizer and other optics. Then you might ask, well, how do you perceive 3D imagery? There are many ways to do it. The simplest way conceptually to think of it is any 3D image can be an assemblage of tiny 3D dots or voxels in space. So if you sort of believe that you can produce a voxel, then you ought to believe that producing multiple voxels lets you build up a 3D image to see. So these technologies can create real images, that is, images that are in a physically accessible volume of space, such as perceived point B. So for each point, you calculate the waveforms that cause these modulators to at least output rays of light that intersect at that point. Likewise, you can project virtual imagery, which is physically inaccessible light or object imagery behind the display by ensuring that the light diverges in a very specific way. So in all, when you want to draw a scene, you create assemblages of these, which in total produce the three-dimensional image. Now, SAW modulators are not new. They've been around since at least the 70s, but work for three-dimensional display is still relatively emerging. So one of the earlier references I've seen is from 1994. Professor Andral and his coworkers in Turkey proposed, wouldn't it be interesting to have a crystal, which through application of sound waves, that is RF energy input by electrodes, which then induces these acoustic equivalent, this surface acoustic wave rippling across the surface, you can then illuminate with a light source and get your holographic image that way. Daniel Smalley and Dr. Bove's team at the MIT Media Lab, working alongside of folks like Wynn Smithwick and other folks, have made these surface acoustic wave devices for holograms. I've shown some references here on the slide. They've done a lot more work than this, but they've made full color SAW modulators in RGB. They've gotten high angular bandwidth out of it, and also an interesting variant in which you extend the length of the SAW modulator and cause the light to emerge from its surface rather than its edge. And we'll talk about that as well. So pausing for a moment, I'll now turn the stage to Michael Moebius. So I think you're going to need to unmute, and he will walk you through the AOM device physics.
All right, thank you, Greg. So yeah, Greg already gave a good introduction of some of the past work in SAW modulators. So I'll dive a little bit more into technical depth of how these devices work and the physics behind them. And really, this is going to set the stage for Draper's goals. So during our program, our goals have really been to expand the modulator field of view and to develop techniques to make these devices tileable as a unit cell to make arbitrarily large displays. All right, so on the top left image here, this is a picture of a modulator that we've actually fabricated and assembled. So the lithium niobate chip that's kind of highlighted here, that is the core piece of technology that allows this display to function. So let's walk through how the light actually flows through this modulator to produce an image and the light field that enables a hologram. So to start with, we couple light into optical waveguides via a diffractive grating. So light comes in and TE polarization on the left, hits the grating, and then gets redirected into the waveguide. Next, we have a interdigitated transducer, IDT, which produces a surface acoustic wave. So this relies on the piezoelectric properties of the lithium niobate substrate that we're using. So when we apply an RF signal to that IDT, essentially the electric field causes the lithium niobate to kind of squinch together and relax together with the frequency of the RF signal that's applied to the IDT. And that'll actually produce a physical ripple that scoots along the surface of the lithium niobate and gets loosely confined in the same waveguide that confines our optical signal. Next, once that light interacts with the surface acoustic wave, there are two things that happen. First of all, the polarization of the light rotates from TE to TM. I'll describe in a few slides why that's important. And next, we also have a diffractive interaction between the surface ripples on the SAW modulator produced by the surface acoustic wave and the light, which causes the light to diffract down into the substrate. So based on the SAW frequency, the light gets redirected at a different angle. So let's step through each of the components that enables these modulators in a little bit more detail. So I'll talk about the in-coupling grating first. So we receive our wafers with the waveguides already fabricated in them by a vendor. So they're basically indiffused waveguides. And we then use our operating wavelength, typically around 630 to 640 nanometers, and the waveguide index profile as inputs for FTTD sims that allow us to, in simulations, optimize the performance of our gratings. So the leftmost figure on the slide shows the coupling efficiency for 3 different guided modes that we can excite in our waveguides as a function of incident angle. So in our devices, we've mainly focused on using the TE1 guided mode to produce our light field for our holographic display. So that gives us a specific coupling angle that we want to shine the light into our modulator at to get our peak efficiency. So next, what we do is we take that grading design and we define it with photolithography and produce an etch mask on our lithium niobate, and then use a physical and chemical etch process with argon and CF4 to literally produce air trenches in our lithium niobate. And that forms the grating that couples our light into the waveguide. So the middle image is an optical top-down figure of fabricated grating, and the rightmost image is an SEM kind of angled image of the etch trenches in the lithium niobate. All right, so next up are the IDTs. So the left figure here, that's a top-down picture of one of our wafers after we've fabricated our IDTs. The right image is a close-up microscope image of a fabricated IDT. So to define these, we've actually used some tools over at MIT, the Heidelberg maskless aligner, because it gives us a very nice balance of enabling rapid updates to our mask that defines the features as we optimize our designs and improve our IDTs. And it also gives us resolution comparable to photolithography and reasonably fast wafer scale fabrication process. Next, we actually deposit a chrome adhesion layer followed by gold to form the bulk of the IDT. And I'll talk about how we decide on the IDT frequencies that we design them to on the next slide.
So Mikhail, I just wanted to jump in for a second, and it might be useful if the participants can see me gesticulating with my hands here. So when we talk about IDTs, for folks who aren't familiar with that, these are interdigital transducers where you have these fingers that are roughly micron scale kind of intersposed with these other fingers like this. And when you assert this 300 megahertz waveform, these physical undulations are induced, as Mikhail said, which then travel across the surface of the crystal. That is the hologram, and that, when illuminated, is what shapes the light fields exiting the device.
Yep. Thank you, Greg. All right, so what we actually use to decide on the IDT frequency is coupled mode theory. So essentially, there's the signal that's produced with the light field. It's actually not produced at all IDT frequencies. It's only produced where this overlap integral, which is a combination of the change in the dielectric tensor that's produced by the surface acoustic wave in the material, the electric field of the guided TE mode, and the electric field of the TM signal that's ejected into the substrate. When that overlap integral is non-zero, that's when we see signal. So the leftmost plot shows a single peak where we would expect to see signal out of our TE0 guided mode. And the second figure shows a series of 2 bumps where we'd expect to see signal out of our TE1 guided mode. So if you move on to the next slide, we've also tested this. So when we measure signal out of our modulators as a function of saw frequency, we do actually recover pretty well the prediction from coupled mode theory. So the TE0 guided optical mode produces signal from about 250 to 300 megahertz RF frequency, and the TE1 guided mode produces signal in 2 bumps, basically, across a broader range of RF frequencies. So that broader range of RF frequencies is what we've decided to use. Yep, can move on. So that's only half the story, right? We also need to be able to predict the scanning or the deflection angle that we get with our signal from our saw modulator. So we need a couple more inputs there. So we're using X-cut Y propagating lithium niobate waveguides at 630 to 640 nanometer wavelength. So for any material scientists out there, you'll know that saying X-cut Y propagating, that gives us a lot of information about how the crystal will interact with the light. So because of that crystal orientation, our guided mode actually sees the extraordinary index of this birefringent lithium niobate crystal. So what that means is the TE guided mode actually sees a lower refractive index than the TM signal that's produced once the light interacts with the saw. So when we have that switch from TE guided light to TM signal, the horizontal component of the K vector is conserved. So now that the K vector is different due to the higher refractive index that the light sees, it'll now dip down into the substrate. And in this K vector diagram, you see that we actually add the K vector of the surface acoustic wave to the K vector of the guided mode. So as we add a larger and larger K vector from the saw, as we crank up that RF frequency, it turns out that our scanned signal is going to come closer and closer to horizontal in that crystal. So if you flip to the next slide. So we can calculate our scan angle in air as a function of saw frequency. And we can also measure that same information by essentially using an optical detector to look at the angle at which we see signal out of our modulator as a function of saw frequency. So the TE1 guided mode will produce scanned signal or scanned output light from about 20 degrees up to 10 degrees from the plane of the modulator.
And I'd just like to point out that, so in the field of holographic display, this is a big deal when Daniel Smalley, who's now Professor Daniel Smalley, when he was at the MIT Media Laboratory and now is at Brigham Young University, showed that you can get this fantastic of an angular span for these horizontal ray fans you could program for across it in the continuum or discretely. This is a fantastic ingredient, fantastic spark plug for display engineers like myself to create interesting displays around. So that's kind of a punchline of that graph on the lower right.
All right, so Gregg is going to be going over these surface emitting displays in more detail later on in the presentation, but I briefly want to touch on how that kind of device is enabled because it requires a little bit more to be added to the modulator. So surface emitting modulators, they're nice because you can have a smaller number of optical and RF inputs, but you also need an extra feature because the angle at which light is ejected into the substrate is so shallow that it will actually be trapped inside the lithium niobate by total internal reflection. So we can only have light escaping out of the end facet of the device in the current configuration. However, if we now add in an output coupling grating to the back surface of the modulator, so if you move on to the next slide, we can use this grating on the back surface to redirect the light at a steeper angle so that it can escape the high index lithium niobate crystal. So next slide. So we've actually also used FDTD simulations to design and optimize our output coupling gratings. And in this case, because of the high index of lithium niobate, it sets much tighter fabrication requirements. So we need to have highly sub-wavelength dimensions of our grating. So for this, we've used the e-beam lithography tool at MIT to define glass ridges using HSQ. So here in the bottom left, we have an SEM image of the glass ridges produced with e-beam lithography. The top left image is a schematic of our grating. So it's basically glass ridges encased in silver on the back surface of the lithium niobate. And finally, the bottom right here is just a nice optical image of visible light diffraction once we've actually fabricated these grating structures. All right, so at this point, I'll turn it back over to Gregg.
Thanks a lot, Mikhail. So what you've learned about is SAW modulators generally, that sort of shorter ones are easily used to emit light from their edge. And if you were to extend them and introduce a mechanism for light to escape, you could then create surface emitters. So let's focus on those edge emitting ones to begin with. In order to assemble these into a display, they have to be slim and they have to be illuminated. So the team miniaturized the illumination and figured out slim packaging. Each modulator channel of this variety today needs a backlight with very precise aiming. So in your living room television, there used to be just sort of one big backlight, then it went to an assembly, say, of several or a handful of LEDs. In this type of holographic display, each modulator channel is associated with its own backlight. And it isn't just shine a laser beam at an incoupling grating, it has to be done within a very, very fine sub-degree precision. So the team developed a number of ways to do this, and what we think is best is a small carrier into which there are fibers and also Grin rod lenses of very precise alignment and coplanarity, and then it becomes a simple matter to light up these chips that have been flip chip bonded onto the circuit boards. Also, speaking of flip chip bonding, that was an additional challenge, which is the same surface of the modulator that has the electrodes on it, and therefore needs to be reasonably flush to the circuit board through a conductor, is also the surface that bears these physical ripples, the hologram. So how do you connect those two without actually smushing the holograms and attenuating them? There are several methods to that that involves the finite height of this conductive epoxy that we use, and also that circuit boards have different layers. The silkscreen and conductive layer are actually different altitudes, so to speak, on the micron scale. So one can act as a porch for the other. Well, let's talk about how you put this all together into some displays. And to sort of bound some expectations here, display technology creation from the first pixel to when a consumer would want to buy it is typically a several $100 million to low $1 billion exercise. And of course, this program is a very generous 4-year IRAD, but is not in that order of magnitude. We had limited funds to do all of these technologies. So consider this a sort of first pixel demonstration. So as a reminder, in this edge emitting display architecture, you perceive points in a 3D image where the constituent beams cross in front or behind, and through linear superposition, you could build up complex images. And the flow from bits to photons to 3D is a first rendering step where some software written in Python, you enter into it where you'd like the primitive to appear that you're projecting. Then it calculates the constituents of a time domain waveform in that band that we talked about. Then these are applied to the light field projection modules, which shape the light from these so-called pixel apertures. And the intersections of those paths are perceived as 3D imagery. So over the last year or two, we built numerous light field projector modules, in the last several months, and verified their fields of view. We're really thrilled that the light field expansion optic, this micro telescope array on the right, worked as we intended. It gives you a 45-degree, very initial addressability of space. These were assembled then. There's about 10 or so of these cards in the display, perhaps up to 14 now, but we're using the first 9 or 10. So in the upper right, you could see a photograph looking edge on to the chassis that holds these cards at a 2mm pitch. We thought that was a good trade-off between how difficult we wanted to make our lives in designing very thin, repeatable light field projector modules, and how coarse you can get away with the pixel spacing and still see an image. And the side view is below, where you could see sort of the fiber optics in kind of clearish color interspersed with the cables that bring information in. Displays of this sort require one information feed per pixel. Now we step back and look at the apparatus. To drive these 9 or 10 cards, there are 10 lasers in the lower right-hand corner. Not shown off to the right of the screen is a chassis with a multiple channel arbitrary waveform generator. This RF drive information feeds in through a network of RF amplifiers and splitters, then goes to the region where the 3D display is, shown by that red dot, down into the chassis of cards. And you might ask, you've got 9 or 10 cards with 8 pixels apiece, why don't you have 70 or so signal sources instead of 10 that then are multiplied? Frankly, this is a proof of concept to get it running. So we limited ourselves based on the budget considerations and time considerations to draw imagery that is all composed of vertical features. So when you give a card a command, all the pixels in that card receive the same command to direct light in a certain way, to shape light in a certain way. So the good news is that the system works. And what we mean by that is this. We have software that allows us to type in the coordinates of where those vertical primitive images are in terms of its X location and its Z location. So if you direct your attention to the left-hand side of this drawing, it's a top view. The display is shown at the bottom. The observer is somewhere off to the beyond the top side of the slide. And if you type in, for example, X equals 95 and Z equals plus 55, it computes the complicated waveforms that are required to project this image in space. So in the upper right, then, it looks like this, where you can project where dots float. That, of course, is a PowerPoint representation. The top view shows the distance, which is 55 millimeters away in this first test case. And in the bottom are stereo pair, cross-eye stereo pair images that allow you to see the image. Now, before I go to the next slide, I'll explain a little bit more about what this means. So this means it worked. Second, this is eight pixels per card. And very often in the field of spatial 3D display during a test phase, experimenters place a sort of physical reference object co-located with the display space of that display, so that you understand where you're converging your eyes and where your eyes are going to be focusing. So here we took an actual screw head and put it into the optical breadboard and told the computer to float a 8 voxel tall line so that when you move your head back and forth, that line will stay fixed above the screw head. And indeed it did. So this is much, much easier to appreciate in person than through a two-dimensional set of photographs here. But as the camera is moved from the right to the left, again, this ordering is to correspond with how cross-eye stereo pairs are usually done. I don't recommend crossing it with this large scale here. You can see that those shimmering dots in front of its background do stay fixed with location to the screw head. So this was a big moment for the team that 4 years of work culminated in the successful display. And of course, there are next steps. So we need to smooth things out. We're going to make scenes with some complexity, like rectangles in the foreground and the background and so forth. This is just sort of first pixel, and you're the first public audience privy to see this result. So you might ask, can you also make a virtual image? Can you make it seem as if scenery is being reconstructed within or even behind the display device? And it turns out the answer is yes. So if you were to type in a negative value for Z, a negative value for distance to the observer, I was able to perceive a line that looked like it was trapped inside of the display chassis or behind the display chassis. And as I moved my head, it stayed right there, which was a really interesting effect. So compelling first steps for the team, and I'm proud of their work. So next, as I said, we'll be composing scenes of lines and rectangles of different depths, enabling some perspective anti-aliasing, and we're good to go. But also, I'd like to return to what Mikhail hinted at, which is, okay, so that's an edge-emitting modulator. What if you were to increase its length in a way inspired by what the MIT Media Lab had published a number of papers on? Could you then create, say, a tablet display with none of these chassis and spacings between the cards? And yes, you can. So in our limited time remaining, we will give you a flavor for what is involved in this next generation of display, which is a surface emitting SAW modulator. So you recall we said there are roughly 2 variants of these SAW modulators, and you just heard about the edge emitting ones. But there's also this emerging work on surface emitting ones. These are attractive because they exploit the long lifetime of the SAWs. This is on the order of 1 centimeter or more as they propagate across the surface of the modulator. And because of that, you no longer need a coax, a wire for every pixel, every millimeter or so. You could then feed in a whole centimeter or more of holographic imagery and then illuminate it when that hologram is physically placed where you want it, and then produce a light field, a holographic image for the observer to see. That gives you lower swap, so to speak. So folks at the Media Lab did a lot of great work towards these surface emitting SAW modulators. And recently they proposed and reported on a variety of methods to fabricate them. So for instance, in the center, in 2017, they suggested introducing a Bragg grating into it to cause the modulated signal to overcome total internal reflection. Whereas you might recall, Mikhail talked about what we did was not to use that approach, but instead place a sub-wavelength grating, surface grating on the backside, which kicks the light out very effectively. So that was our approach, and we took a more microlithographic approach generally to fab overall. And so we're really excited to coax operation out of our modulators in late 2018. And as far as I know, it was a world's first. The vision here, because sometimes folks say, well, I kind of get what you're doing with one row segment of a hologram. How do you make a display? Well, you would go ahead and tile this. So you take a wafer lithium niobate, fabricate the features you need, apply the illumination and drive signals, and then out from this sort of optical sandwich emerges a three-dimensional image. So as you recall, the scheme here is to get light fields from electronically induced holograms, but to enable the light that's been modulated to emerge from the surface rather than the edge of the display. A photograph of the device is shown here underneath the device layout, in which we went with an incoupling prism just to get this first experiment to work. There was several interaction regions. We excited one of them, which had a length of 9 millimeters, and light would pop out sort of out of the plane of this display drawing here. So quickly going through a manual animation of this, light is introduced into the device into its waveguide. And meanwhile, a signal, at first just one little blip of a single frequency-ish sine wave, zips across at several thousand meters per second. They interact, creating a diffracted signal, which is then outcoupled by an outcoupling grating and goes into air. So you can see then that if you were to apply a single frequency SAW, which then acts like a diffraction grating, so to speak, at one main frequency, you should be able to direct the angle of that one frequency component out into air. And that's what this plot here shows. So the x-axis is the data for driving at that one particular sine wave frequency, and the y-axis is the angle in laboratory coordinates that we perceived that light coming out. Then, if you were to change or increase the frequency of that sine wave, the angle, the dip angle inside the modulator, and hence the angle as it escapes into air, ought to change to give you a new angle and also a new exit point. And that worked as well. So this is a plot where we reveal various graph cuts of as you change that frequency, that the light is detected at different places. And of course, that is a compounding of it exiting at a different location, but also having a different angle. And in slides that we're going to run out of time before I show them to you today, we were very careful to tease those apart so we understand the angular component and the translational component in time of each of these effects. Now, can you go farther? Recall I said you could treat this as a linear hologram. You could shout, so to speak, a lengthy signal into this crystal, and it propagates along, and you strobe the light where you want it, and the light field emerges. So you can apply multiple Hogels and a space and another Hogel and a space and so forth. And that worked as well. So here you can see them emerging at different angles in the laboratory frame. Furthermore, you can have high frequency ones, low frequency ones, and ultimately compose them. So before we wrapped up that brief experiment in late 2018, we asked ourselves, can we pack a lot of these Hogels into one system and successfully reconstruct them? And yes, the team was able to do that. Here we had 9 features, which was several emissive or several diffractive regions separated by spaces. And there's a paper cited in the lower left if you'd like to learn more about this promising technique. So to wrap up, we've heard about edge emitting modulators today as well as surface emitting modulators. This was fabricated with quite standard microfab processes. As you heard, we explored the system of X-cut Y propagating lithium niobate. We got 8 millimeter long linear holograms in this first device, and that I think was limited not by the attenuation of the SAW as much as just our incoupling prism was in the way from it getting further and the distance to the IDT. And the team successfully loaded it up with arbitrary waveforms and partitioned it into Hogels. Now, a challenge of the surface emitting variant that is less of a challenge for the edge emitting variant is that the angular subtense, the amount of angle you can project into, is much more modest, on the order of a degree or less than a degree. So it begs the question of how do you make a 60-degree field of view hologram if natively the device is only outputting a degree? Well, there's a few parts to that answer. One is we drove it with a very limited drive bandwidth just to see if the principle worked. And as you increase the drive bandwidth, your angular range increases. Second, we have methods of time varying very slightly the color of the illumination. So they're perceptually equivalent or similar, but on a physics basis, when it hits a diffraction grating, the diffraction grating will do its job and send light out at different bore sites as a function of time. So you get sort of coarse control of the bore site as well as fine control provided by the RF information. And then finally, one could associate any number of light field expansion stages to it to then go from 5 or 10 degrees subtense up to 45 or 60 degrees subtense, such as we did with the edge emitting display demonstrator. So I believe we reached the end of our talk. So in summary, the team developed the full stack of technologies over the last 4 years, everything from integrated optics in custom SAW, AOM fabrication, and so forth, the microfab of those pixel microstructures that included the transducers and the in and out coupling gratings, electromechanics for how the modulators are flip chip bonded and stacked appropriately, all the way through precision fiber and rendering software. So I know we're moving on to Q&A, but any of you in the audience also should feel free to email me directly at gfavalora@draper.com. Thank you very much.
Well, thank you, Greg and Michael, for this very interesting talk on technology. And now we are open for questions from the audience. So there are 3 in Q&A. So first one, I just make to sure, Greg, that so you connected with Joseph Burns, correct? So like he was just saying hi, okay?
Hello.
Yeah,
good to see you outside of Facebook.
Yeah. Okay. The second one is from Alfred Tang, and what he's asking is if this technology can make movies or just still pictures. But I would maybe ask you something closer. So I understand you have done these demonstrations, and you mentioned you can make these points appear in specific coordinates, but do you have a refreshing rate? Can you, in principle, make those like points move around? It's sort of in the spirit of what Alfred was asking.
Oh, great question. I think those questions make a lot of sense. So yes, absolutely, these technologies will be capable of animation rate field updates. That is absolutely not an issue for these systems where the surface acoustic waves propagate at such great speed. And frankly, the computation underlying it is not complex at all. So just as a matter of how we time phased our work, we just wanted to get individual primitives working, such as these vertical lines. We debug that, we improve their interperspective qualities, and then after that is to see how we can get the animation rates going. That's frankly more of a question in the near term of how well do I write in Python as opposed to what can the system do. Okay,
so it's not a hardware issue, but how if you can exploit the potential of the hardware.
Right.
Okay. Okay, so let's continue. And there is a question from Xiong Yang about package and contact. So I guess you gave your email address, and they can contact you if you want to share more information or anything, right? Because I believe we have a recording. We'll have a recording on the website, but I don't remember the terms under which that is shared. So I think that's a far easier way to go about is to contact you, right? Okay.
Yes.
Okay. Then from Robert Ashcraft, what do you expect the input information bandwidth required to drive a display at commercially relevant resolution?
I don't have an off-the-cuff answer for that. I mean, it would be higher ultimately than a typical display, although it's a lot more tractable than you might think it is. So for example, even back in the year, I don't know, 2002, when I was doing a startup called Actuality Systems, where customers had to render an XJ resolution from image from between 100 and 400 points of view, even GPUs of that era were able to do it. So frankly, I think really the engineering effort is how do you get all the interconnects into place? How do you position the processor elements and so forth? The actual processing itself is a lot more tractable because you don't have to compute, sorry that I'm pausing for the right words here. I think the MIT Media Lab folks used to call it diffraction-specific computation. So that is, you compute it from numerous viewpoints, say 50 different viewpoints at once. That's really the limiting factors, your ability to render high polygon count scenes in 50 different viewpoints at once. And then it's sort of a summation of what comes after that. We're not modeling interference and diffraction effects through air and doing all of that at all. This is really kind of convolving brightness per perspective with an underlying frequency at which we drive the saw. Maybe more easily answered in email than in real time in a seminar.
But let me ask you a follow-up question that I think is related, because you, if I understood well or recall well, you mentioned that you had this great opportunity to do work on the matter because of, let's say, time and resources, right? Maybe an IRAD was that?
Yeah, it's an IRAD.
But then you say, you know, the displays takes all this effort and money. So how, in terms of that, what do you say? It's a 10-year thing, or there has to be like significant investment? I don't know. Can we have like a holographic display like Star Wars sometime soon?
What's the joke? It's like people in my field, the answer is always, oh, in 20 years. I think it's a lot closer than 20 years. Frankly, it comes down to which external parties have the interest and the budget to sort of jointly climb up the TRL ladder here. Because really the team has proved out a huge number of the underlying enabling technologies. Now it's largely a practice of size reducing the RF, size reducing everything else, and getting the packaging right. So it could be in a several year time frame.
Okay. So continuing with the Q&A, there's a question from Paul Bonsen. Is this work continuing towards commercialization for early usage cases? So I guess, like, I don't know what's the end goal of the current project, and maybe you can tell us a little more about that, opportunities for follow-ups.
Sure. So hello, Joost. Good to see you today. Yeah, so I can't go into a lot of detail about efforts to commercialize or externally sort of sponsorize the work, but certainly you can imagine a lot of applications. So in the military domain, there are ways to visualize missions as they play out. There are all sorts of aircraft-related applications of this technology. And also outside the military domain, everything from oil and gas visualization to even entertainment are all being considered. And I think it'll take a joint approach where companies with interests and understanding of display technologies I would welcome working with them to bring this up to TRL, so that one day it's something that folks could buy for enterprise or consumer or other use.
Okay, there's one more question in the Q&A. It's from Tyler. He's asking, are you able to make IDTs and gratings with multicolor diffraction capabilities? I actually had the same question. I don't really know too much about photonics, but I was wondering if some multicolor display was at hand. So Tyler explained it so much better than I could.
Absolutely, that's a great question. So maybe the question is, will these work in color or in full color? Yes, and I very quickly mentioned that in the beginning of the presentation. One of our collaborators, Daniel Smalley, a professor at BYU, had, I believe when he was at MIT, or maybe he did it at BYU, showed RGB operation. They figured out a number of the technologies for that and proved it by showing this beautiful picture of a butterfly projected from the modulators.
Okay. Well, thank you. So I think that's the end of the did I? Oh, maybe there's one more. So let's do one from Justin, but let's start maybe in a minute or so we don't hold people beyond the plan. So from Justin, he's saying, wonderful presentation, Gregg and Michael. Congratulations for your success. The line demonstration is awesome, but once further progress is achieved, what is your personal Hello World example you want to display?
I love that question, and I wish I had a good answer. Boy, we sure get a lot of Star Wars jokes, about things we might project. Personally, I thought if we have a low pixel rate display or low pixel count display, it'd be fun to play Pong in 3D because that really plays upon the depth effect. But we'll have to see. I welcome suggestions for the first real great imagery to project out of a holographic video system like this. Thank you.
Okay, thank you again, Gregg and Michael. Excellent job, and I think there was like a lot of interest and follow-up questions. I hope they contact you. And for the rest of you, well, thank you for attending the MTL seminar. and I'll see you on December 2nd at the doctoral dissertation. Thank you again for your time.
Oh, our pleasure. Thank you so much. Thanks for joining us today.